All right. So we get started today on chapter 15 here, talking about chemical equilibrium. Before we do, see if there are any kind of questions or things people might have about the course itself, material we've covered, or anything. All right. So as just kind of a reminder, right, kind of timeline of things as well. Screen here. Oh, no, wrong one. Right. For this week here, right, we have chapter 16 that will start next week. And the week after that, we'll finish 16 and start a little bit of chapter 17. Okay. And then at the end of the month, we'll have exam number 2. Okay. Right. So there'll be a quiz, right, due this Friday. Reminder, right? Homework for chapter 15, right? Quiz on 15, right? Homework's due a week from today on sapling, right? Yeah, type of a thing. So again, all this stuff is put on the Canvas website. Hopefully people have been going to there. I mean, obviously you need to take quizzes and things like that, but checking out, right, the homepage, the syllabus, right, have linked everything that's kind of required, as well as then links to the modules, which have links to the lecture videos and things like that related with the course. Okay. So again, if you haven't been watching the videos that I post online, I suggest you do so because they are different from what we're doing in class. Right, the lecture videos I do online, doing the example problems, but I talk in detail about the concepts and ideas behind the material that we talk about in class, right, that lead to why we do some of the things we do and the examples that we do in class and such, okay? Right, in class here, again, we're highlighting some specific concepts and ideas and then doing plenty of examples in class, okay? Yeah, so those lecture videos are different from what we're doing in class. Okay. Sort of like reading the book, right, is just extra material to help learn things that are covered in this class. Okay. Yeah. And that's kind of it for announcements, right? Keep remembering to go to SI sessions. Okay. Again, because at most you can attend 2 sessions per week, okay? And we're already getting close to the half, I think. Am I roughly accurate about that, Riley? Yeah. Yeah, so you have 6 by now if you're going every single week. If you miss the first 5, then you better start going to 2 per week because that's the only way you're going to get all 10, right? But hopefully you've not been doing that, right? Yeah, so that's it for the announcements. Any comments, thoughts, questions on anything I have to say? All right, so let's get going here on chapter 15. So this is sort of different than kinetics, right? Different from some of the things we've been talking about. But we'll be talking about chemical equilibria for most of the rest of the semester. Okay, it will be on exam 2. Chemical equilibrium will be relevant to everything we talk about with exam 2 when we talk about acids and bases and things like that. Chemical equilibrium will be relevant to that as well. And on exam 3, it will still be part of chapter 17 and things that we'll talk about there. Okay. And so for a good month or more, we'll be talking about this topic directly in chapter 15, indirectly, even when we talk about acids and bases, and talking about weak acids and weak bases, and talk about titration and all this other stuff. So chemical equilibrium will be around for a while, okay? Basically until we get to thermochemistry and electrochemistry. All right. So how would one describe chemical equilibrium, right? How would you describe a reaction that is at equilibrium?
When the forward reaction and the reverse reaction.
Yeah. So if we have, right, and we just have some reaction here, A, right, going to B, right? Then equilibrium, at equilibrium, right? Rate in which A is being consumed, form B is equal to the rate at which B is being consumed to form A, right? In our chemical equilibrium reactions, right, we have A, reactants going to products, okay? But products can also go to reactants, right? And while we haven't really discussed this idea before, right, every chemical reaction can technically go in either direction. Now, typically, chemical reactions we've talked about are ones that are so dominant in one direction that we just think of them as unidirectional reactions, right? They just go one way, they aren't going to go back. But any chemical reaction can go either way, right? So a chemical reaction is breaking some bonds and forming new bonds, right? Well, I can just undo what I did, right? If I had like little microscopic tweezers, right, I could just move the atoms back to where they started, right? And so any reaction can go back to where it was, theoretically, right? But not all chemical reactions will go in the reverse direction because it just might be so difficult to do so. It's just never going to happen, right? And so often, for lots of reactions, we describe them as equilibrium reactions because they really just go one way, okay? Because the reverse reaction is just, not ever really going to happen. So it's not an equilibrium reaction. But there are plenty of reactions out there where reactants form products and products form reactants, and both of those reactions, right, A going to B and B going to A, can happen, and they potentially happen at similar rates, and those reactions reach equilibrium when the rate of A, right, in which A is being consumed, right, the rate in which A is being consumed is equal to the rate in which B is being consumed, right? Okay. And so the rate of that forward reaction and reverse reaction equal, right? Our forward reaction, you want to think of it, right, for this equilibrium reaction, our forward reaction, as we'll talk about it, right, will be, A going to B, and the reverse reaction, right, is B going to A, right? Right, and so the rate of the forward reaction is equal to the rate of the reverse reaction when we reach chemical equilibrium. And then what can we say about concentrations of our species at equilibrium? Right, so we talked about, right, equilibrium means that the rate of the forward and reverse reaction are equal, right? But what else happens at equilibrium? The concentrations are constant, don't change, right? So our concentrations, right, of our reactants and our products stop changing once we reach equilibrium, okay? All right, and so pictorially, right, you can look at, say, concentration versus time, and then the rate of your forward reaction and reverse reaction versus time. So the reaction here is, well, it's not written. It's N2O4 decomposing into two NO2s, okay? It's N2O4 going to 2NO2, right? And so the rate of our forward reaction, right, is given by its rate law of Kf times concentration of N2O4. The rate of the reverse reaction, so I can write out the reaction just so it's clear here. Our equation here is N2O4 O2 NO2. Right. So that's our chemical reaction, right? N2O4 going to 2NO2. Okay. Right. So that these are elementary reactions. It's directly describing what's happening. So the rate law is just related to the rate constant times concentration of reactants. Okay. For the forward and the reverse reaction. Okay. But right, so the rate of the forward and reverse reaction once we reach equilibrium are the same, and they're non-zero, right? A zero rate is down here. The reverse reaction has no rate initially because there's no initial concentration of the products, right? I'm just starting with the reactants. Okay, right? Concentration of the products, NO2 starts at 0. So the rate in which those are consumed is equal to 0 because there's none to consume. Okay. But when I reach equilibrium, the rates of forming NO2 and the rates of forming N2O4 are equal, right? And so the concentrations of NO2 and N2O4 remain unchanged, okay? Right, and so this chemical equilibrium is a dynamic equilibrium. It doesn't mean things have stopped. It means just no net changes are occurring anymore, right? But things are still happening. Your reactions are still happening. They're just happening at equal rates, okay? Right, sort of like, you know, if you fill up water into a sink, right, and then you allow the water to drain, if the water flowing into the sink is flowing at the same rate as the water flowing out of the sink, right, the height, the volume of your water in your sink is unchanged, right? And so that's the same thing with a chemical reaction, right? If the rate in which A is being formed is the same as which it's being consumed, right, there's no net change in the concentration of A, right? While, right, in your sink, new water is flowing in, old water is flowing out, right? It doesn't, right? So there's water that's being changed within your sink, but the total volume of water in your sink is unchanging as long as the inflow and outflow of that water rates are the same, okay? So again, it's the same type of thing for chemical equilibrium, right? The rates of formations of your products and reactants are the same. So the concentrations are not changing, even if individual NO2s are still reacting and individual NO2s are still reacting. The total concentration is unchanged. Questions about chemical equilibrium? Its definition, what it is. All right. So at equilibrium, what do you think? The reaction stops. Concentrations of reactants and products are equal. Concentrations of reactants and continually decrease, or the rates of the forward and reverse reaction are equal. So it's some B's and D's, right? So for a reaction at equilibrium, right, as we talked about, right, the rates of the forward and reverse reaction are equal, right? The rates in which A is being consumed, that's the rate of the forward reaction. The rate in which B is being consumed, that's the rate of the reverse reaction, are equal, right? Now for B, this could be true. It could be that you have the same concentration, same concentrations of reactants and products, but in general, that does not have to be true. So in general, right, the concentrations at equilibrium of your reactants and products can differ and will typically differ. It's a lot more likely that the reactants and products concentrations are not the same at equilibrium than they are. Now it is possible for them to be the same, but often they're not. So yeah, and then the reactions definitely don't stop. They are still occurring, okay, and the concentration is not changing once reaching equilibrium, okay. So it's D here, right? The rate of the forward and reverse reactions are equal, okay. Concentrations are constant, but they are not necessarily equal to each other, okay. The reactions have definitely not stopped. All right. So for every equilibrium reaction, we can write out what's called an equilibrium constant. Okay. Write out what we call our equilibrium constant expressions. Okay. So we have a couple of example reactions here. Okay. And so for these examples, what would be the equilibrium constant expressions for these guys? Again, post. I'll use this point as a reminder, right? Again, the videos for chapter 15 are post, you know, at least by the Friday before we start talking about this stuff. So people have time to start watching some of these videos. Okay? So that hopefully, right, we feel like we have an idea of how to answer some of these questions, right? So for this, right, equilibrium constant for the reaction 2NO2 going to N2O4 is going to equal what? Over NO2 squared. Okay. What about the second one? O squared, Cl2. And the final equilibrium constant? Yep. Right? Exactly, right? And so, right, what is the pattern, right, that we're doing here for each one of these equilibrium reactions? What are we putting in the numerator here? Our products, right, go in the numerator of our ratio, and in the denominator, right, it's then the reactants. Okay. And then what am I doing with the stoichiometric coefficients? Goes to their powers, right? So if a stoichiometric coefficient of 2, power of 2, right? Stoichiometric coefficient of 2, power of 2. Stoichiometric coefficient of 3, power of 3, right? So, right, exactly, right? The general form of our equilibrium constant expressions for every equilibrium reaction, okay? In the course of talking about chemical equilibrium, right, when we talk about acids and bases, we're going to like say like Ka, Kb, Kw, let's see, Ksp. We're going to talk about Kc, Kp. We're going to use these little subscripts here, okay, on our equilibrium constant expressions. They're going to indicate the type of equilibrium reaction we're talking about. But in the end, they're all just equilibrium reactions. So in the end, for every one of these reactions, right, every equilibrium reaction you ever see, right, the equilibrium constant is related with the concentrations of the products over the concentration of the reactants, raised to their stoichiometric coefficients. Okay. Now there's one more rule I'll get to. Okay, so here, now, talk about what the equilibrium constant expressions are for these reactions. Where now I've explicitly written out here what the phases are of our different reactants and products. All right. So we have, right, PbCl2 solid going to Pb2 plus, aqueous plus 2Cl minus. What is the equilibrium constant expression going to be for this reaction? Close. Yep. So yeah, that's going to be the rule. So right, so for this one, it's going to be, yep, and then this one, 1 divided by CO2, right? So in all three of these reactions, again, we did products over reactants, but we did not include any solids in our equilibrium constant expression. And the same thing goes for liquids, okay? You never include liquids and you never include solids. You include aqueous compounds and gases, okay? That's it. So aqueous and gases you include, solids and liquids you do not include, okay? But it's products over reactants raised to their stoichiometric coefficients, ignoring solids and liquids, okay? And the reason we ignore solids and liquids, right, is because, right, the concentration of a solid is just equal to its density, basically, right? You do some conversions of moles and to grams using molecular weight, and the concentration is related with the density of the solid, right? Well, the density of a solid does not change as you're using up some of that solid, okay? So it's just a constant, right? And so during the course of your chemical reaction, the density of your solids and liquids do not change. But when I talk about, say, the concentration of a gas, well, the volume that a gas occupies stays the same, even if I use up some of that gas. So its concentration will change. Similarly, right, if I talk about lead, say 2 plus aqueous, right? This is dissolved in water, right? As I use up the lead ions, the amount of water is the same, right? The concentration is the moles of Pb2 plus, right, divided by the liters of H2O, right? Well, the volume of water is not changing during the course of my reaction, but the moles, right, of lead will change, so the concentration does change during the reaction, okay? So that's why we include gases and aqueous compounds, because those change during our reactions. Their concentrations do. But for solids and liquids, the concentrations do not change as the reaction takes place, and so we just ignore them, okay? They're just constant, so it doesn't really matter in the end, so we just ignore them, right? Okay. So our equilibrium constant expressions are products divided by reactants, right, raised to their stoichiometric coefficients, ignoring solids and liquids, okay? So do some more examples of this, right? So in the chapter 15 examples, they're handed out in class today. If you don't have them, there's some extra up here, as well as the participation questions if you want to come up to grab it. Okay.
I have a question.
Oh,
Oh, I just had a quick question.
go for it.
Oh, okay. For the last slide, for like the CaO plus the CO2, why was the K written as like 1 over CO2?
Because in this last reaction here, right, CO2 is a reactant, and so the reactants always go in the denominator, right?
Oh, okay.
Yeah, and so that's why. So CaCO3 is a solid, so it doesn't appear. So there's no products appear, so it's just 1, right, for the products, and then in the denominator are your reactants, and the reactant here that's not a solid or a liquid is just CO2 gas.
Okay, thank you.
It ends up being 1 over CO2 gas. Other questions? All right. All right. So now we have some of these other examples here. Okay. Looking at writing out the equilibrium constant expressions for these guys. And if these examples, are given on Canvas. They're handed out here in class, and if you attend class on Wednesday, I'll hand them out as well. Right? So we got this example, writing our equilibrium constant expressions. So for this first reaction, K is going to equal what? Over NO, right? N2O times NO2 divided by NO cubed, right? Because again, products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients, including only gases and aqueous compounds, right? Ignoring solids and liquids. Okay, everything is here gas, so everything is included. So next expression. Again, everything here is aqueous or gas, so we include all of it. Products or reactants, everything has a stoichiometric coefficient of 1, so we don't need to write any other powers out. Okay, right? I'll just note that this happens to be an expression for like a weak acid. So like when we talk about acids and bases, we'll give like these Ka expressions, which we just put this A here to indicate that this is an equilibrium constant for a weak acid reaction. Okay, but again, we don't worry about that here. I'm just kind of pointing that out, right? Because I don't want people to kind of get thrown off when we start writing Kas and KSPs and all this other stuff, because it's just talking about equilibrium reactions. Okay, we're just specifically talking about certain types of equilibrium reactions. Okay, and that's what these subscripts indicate. But again, for now, I'm going to kind of push that aside, just kind of giving you a heads up as we get there in future chapters. Okay. All right, and then this final expression here, equilibrium constant, is going to be what? Ag plus and Cl minus. Thank you. All right, and I do not include the AgCl solid because it is a solid. Okay, so just as products that appear in the expression and none of the reactants appear in the expression. Okay, it's just AgCl solid, Ag plus and Cl minus. That's all that appears. So any questions about writing out these equilibrium constant expressions? Okay. Hopefully, if you do, please ask them, because we're going to be doing plenty of this, right? Not just in chapter 15, but in chapter 16 and chapter 17. We're going to have to write out these equilibrium constant expressions, and especially when we get to chapter 16 and 17, there's going to be a lot more stuff that we're potentially doing besides just writing these out. So we should be comfortable with them now, right? So going forward, every time we see an equilibrium reaction, we can just immediately write out what that equilibrium constant expression is. Okay. So any questions? All right. So I'll have one here for you. Which of the following equilibrium constants are not correct, given the corresponding equilibrium reaction? So people saying D here, and why is D not correct? Exactly, right? So right, D includes water, H2O, which is a liquid, and that should not appear in the expression. So it should just be H2CO3 divided by CO2, with water never appearing. Okay. Yeah, so D here is the only one that is not correct. All the other ones are the correct equilibrium constant expressions for those equilibrium reactions. Any questions about these? All right. So every equilibrium constant, so before we kind of get this example, just kind of point out the fact that, right, So these equilibrium constants, right, express a ratio between your products and your reactants at equilibrium, okay? And that ratio is always the same. So this equilibrium constant for a given chemical reaction has some numerical value, and that numerical value does not matter on what your initial concentrations of your reactants and products are. It's always the same number. Okay? So for example, reaction A here, let's say, has an equilibrium constant, you know, that's the expression, and that equals 1,200 or something like that, right? K equals 1,200, right? Well, the ratio of products to reactants is always going to be equal to 1,200 for this equilibrium reaction, no matter what initial concentrations you start off with, okay? Does not matter. When you reach equilibrium, the ratio of NO2 times NO3 divided by N2O5 will always be the same, okay? Now that ratio is different than the ratio for a reaction in B and C, right? So each equilibrium, right, has its own equilibrium constant expression, which has its own numerical value, right, for what that equilibrium constant equals, okay, right? And again, it's independent on your initial values, okay, right? So here, I have this example where I have this equilibrium reaction, okay, PCl5 going to PCl3 plus Cl2. Now it has an equilibrium constant AP here. So P, the subscript P, is just indicating that we're dealing with pressures. Okay, that's what that P is telling you, that we have gases, we're dealing with pressures. Okay, so that's right, because in the problem it gives you partial pressures. Okay, so the Kp is telling us we're dealing with pressures, right? So Kp is 0.497. Okay. Now, at equilibrium, you are able to measure, right, that the partial pressure of PCl5 is 0.860 atmospheres, and the partial pressure of PCl3 is 0.35 atmospheres. But you can't measure the partial pressure of Cl2. So the question is what is it? What is that partial pressure of Cl2 at equilibrium? Okay. All right, so let's look, working over this example together. I have one student on Zoom here. They got an answer of 1.22, and let's find out if that is what it is. Right, so, right, every equilibrium problem that I ever deal with, right, I have some problem that has some chemical reaction that's in equilibrium, right? I know it's an equilibrium reaction because it's got that double arrow written, right? If it's not directly stated in the problem, right, if the reaction's written with those equilibrium signs, okay, then I know it's an equilibrium reaction. Now here it's also talking about it's an equilibrium mixture, right? So I know it's an equilibrium reaction. So for every equilibrium reaction, the first thing that I can do, right, is write out what the equilibrium constant expression is for that reaction. Here I'm going to call it Kp, because we're going to deal with pressures, okay? And so for this reaction, what is the equilibrium constant expression equal to? Yeah, so it's going to be dealing with the pressure of Cl2 times pressure of PCl3 divided by the pressure of PCl5. Okay. Now again, right, we include gases and aqueous species in our equilibrium constant expression, right? For gases, I could talk about the concentration of the gas, right? The number of moles in the volume that the gas occupies, but I could also talk about the pressure of the gas, okay? And so, well, all the examples we've done so far, we've just focused on using concentrations. For gases, I can use pressures. If I do, I indicate that I'm using the pressures by having this P here, right? Kp, okay? So this P stands for pressure, right? Not the phosphorus that's in this reaction, okay? This P has nothing to do with the chemical reaction dealing with phosphorus, okay? That P is indicating pressure, okay, in your equilibrium constant expression, okay? Right? Well, this equilibrium constant expression tells me, right, at equilibrium, the ratio of Cl2 times PCl3 divided by the pressure of PCl5, right, that ratio has to equal 0.497. Okay? Always, every time, once equilibriums are reached, that is what that ratio will always equal. Okay? So I just need to plug in for the pressures that are given in the problem to solve for the pressure that I need to solve. Okay, right? So we're looking for the pressure of Cl2. Pressure of PCl3, we're told, is 0.35 atmospheres. The pressure of PCl5 is 0.86 atmospheres. Okay, that's given in the problem, right? And that equals the equilibrium constant, which is 0.497. Okay, right? Equilibrium constants, by the way, I haven't said this yet in class at least, right? Equilibrium constants are always constant. Okay, right, sorry, I haven't said they're always constant. They're always unitless. That's what I meant to say. They never have any units. Equilibrium constants are always equal to just some number. They're unitless. Okay. Now I know pressures are given in atmospheres, concentrations are given molarities, right? How this is gotten around is technically like each one of these pressures in this expression, I'd want to divide by like 1 atmosphere, right? But basically, like units, just ignore them when dealing with equilibrium constants. Okay. So one time I'll tell you never care about the units because unitless, right? Because how one would write this out if you're being very particular, okay, is you'd say this is like the pressure of Cl2 divided by 1 atmosphere, okay, and then the pressure of PCl3 divided by 1 atmosphere, and then the pressure of PCl5 divided by 1 atmosphere, okay. Right, you take each of your pressures divided by an atmosphere, take each concentration divided by a molar. That then gets rid of the units, but doesn't change the overall number, right? Okay, but we're never going to bother writing all this stuff out, right? We just write this, okay, and then just ignore the units when plugging in, okay, and dealing with the equilibrium constant expression, which again is a unitless number. Okay. So going back to solving this problem, right? I then just need to solve for PCl2. So I multiply by 0.86 over here, divide 0.35 over there, right? Get PCl2, pressure of Cl2, right? Is equal to 0.497 times 0.86 divided by 0.35, which ends up being 1.22 atmospheres. Okay, so move that up here. Right, so the partial pressure of Cl2 is 1.22 atmospheres in this equilibrium mixture. Okay, and we know it has to be 1.22 atmospheres because that is the partial pressure that satisfies our equilibrium constant expression, which is always satisfied at equilibrium. Okay, at equilibrium, those ratios of pressures of Cl2, PCl3, and PCl5 are always going to produce a numerical value of 0.497. So I know that the partial pressure of CO2 at equilibrium has to be 1.22 atmospheres, because that's the only partial pressure that satisfies this relationship, given the partial pressure of PCl3 is 0.35 atmospheres, and the partial pressure of PCl5 is 0.86 atmospheres. So questions about this problem, how we got 1.22 atmospheres, why we set it up the way we did. All right, so right in chapter 5 in Gen Chem 1, for those who remember it, talked about how you can manipulate a chemical reaction, and that manipulates the enthalpy change for that reaction, okay? Right? If you multiply a reaction by a coefficient, you'd multiply the enthalpy by that same number, right? Flip a reaction, you flip the sign of enthalpy. Add two reactions, you add the two enthalpies, right? For those who remember that. Well, for equilibrium constants, it's a little different, okay? If I multiply a reaction by some number, I take the equilibrium constant and raise it to that number. Okay, so I multiply my reaction by 2, take the equilibrium constant and square it, right? Raise it to the 2 power. Multiply my reaction by 3/2, I'd raise my equilibrium constant to the 3/2 power. Similarly, if I reverse a reaction, I don't flip the sign. Instead, I take the reciprocal of that equilibrium constant, right? The reciprocal means I just do 1 divided by the equilibrium constant, okay? And if I add 2 reactions together, I have to multiply the equilibrium constant together. Not add them, but multiply them, okay? Right? So these are the rules for manipulating chemical reactions and how that then manipulates the equilibrium constant values, expressions, okay? So do an example of this, right? Where here I have some chemical reaction H2SO3 going to H plus HSO3 minus. And just assume all these things are aqueous. Okay? And has the equilibrium constant equal to 1.7 times 10 to the minus 2. The question is what is the numerical value of the equilibrium constant for reactions A here and B, right? H plus HSO3 minus going to H2SO3, and 3H2SO3 going to 3H plus 3HSO3 minus. All right. Right, so I'm going to call this reaction here reaction 1. I'm going to call this like K1, right, is 1.7 times 10 to the minus 2. Right, so for reaction 2 here, H plus HSO3 minus going to H2SO3. How would I calculate that equilibrium constant, right? Its value based off of the value given here for K1. So this is going to be 1 over K1, right? Because I flipped my reaction, so that flips the equilibrium constant expression and value, okay? So So this is going to be equal to 1 divided by 1.7 times 10 to the minus 2. Ends up being 58.8. Okay, that's what the equilibrium constant is for this reaction A here. Okay. Then what about for reaction B here? How is that equilibrium constant related to the original equilibrium constant of the above reaction here? Again, I'm calling reaction 1. Yeah, so it's at K1 cubed, which is 1.7 times 10 to the minus 2, the 3 power 10, which ends up being 4.91 times 10 to the minus 6. Okay. Okay. Right. So again, right, I multiplied this reaction by 3, which means I had to take the equilibrium constant and raise it to the 3 power. Okay. I flipped this reaction to get this reaction. So that means I have to take 1 divided by my original rate constant to get my new, or sorry, not rate constant, new equilibrium constant. Okay. All right. Questions about why we did these changes, how we got the values we got? Right, the lecture videos online go into more detail showing you why flipping a reaction or multiplying by a constant ends up raising powers to the equilibrium constants or taking 1 over the equilibrium constants. So again, I very much recommend checking out those videos to see in more detail why we're doing what we're doing, right? How did we get these rules? Where do they come from, right? Just worked out and talked more lecture videos online. All right. So, all right, so far we've talked about equilibrium reactions. What are they? We talked about equilibrium constant expressions. How do we write them? Okay. We talked about the numerical values of equilibrium constants. Okay. And just want to mention, okay, that for these numerical values, right, that we deal with, the magnitude, the size of those equilibrium constants are important. Okay. For equilibrium, size matters, right? Right, because for equilibrium constant expressions, if K is much greater than 1, okay, that means that your equilibrium is favoring products. Okay, let's think about this, right? If where's one piece of paper here? Right. Right, K, or equilibrium constant, right, is concentration of products, right, over concentrations of reactants. Right? So if K is much, much greater than 1, right? 1,575,000, blah, 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 right? Some big number, okay? What that's telling you, right, is that in this ratio, I got a lot more stuff on the top than I do on the bottom, right? So that this is saying I favor products, right? Similarly, if K is much, much smaller than 1, right, then that means I got a lot more stuff in the denominator, right? The reactants are much, much greater quantities than the products, right? And so I'm favoring reactants, right? And so the size of the equilibrium constant can tell you at equilibrium, what should I expect to have more of, right? My equilibrium constant is much greater than 1. At equilibrium, I should expect to have a lot of products and very little reactants. My equilibrium constant is much, much less than 1, then I should expect at equilibrium to have a lot of reactants and very little products. Okay. All right. And so the size of the equilibrium constant can tell you a lot more about the chemical reaction and what to expect at equilibrium. Okay. And this then is related with the reaction quotient. Okay. Now, what is the reaction quotient Q? What is the expression of that? What does that equal for equilibrium reaction? All right, if I had equilibrium reaction, let's see here. So I already have one typed up. I just need to click, right? So if I have this equilibrium reaction down below, right? The lowercase numbers here are representing coefficients. The capital letters are representing the species, the chemical species here. So how would I write out Q for equilibrium reaction? Yeah, close. So for that equilibrium reaction, right? C to the C power, D to the D power, right? A to the A, B to B, right? If you look at this, hopefully think to yourself, well, that looks an awful lot like K, and it should, because the expression for Q is the exact same thing as K. Okay, so the reaction quotient Q and the equilibrium constant K have the exact same expressions, exact same equations, right? So in our examples, right here, right, 3NO going to N2O plus NO2, right? The reaction quotient Q has this exact same expression as my equilibrium constant. Okay. So right, the difference between your reaction quotient and your equilibrium constant, okay, is that so reaction quotient is the same expression as the equilibrium constant, but the values plugged into the reaction quotient are not necessarily. Necessarily the finger off on the keyboard. Okay. What the? Huh? What happened there? Just get rid of all animations on this slide, so I don't know what's going on. All right. There we go. Right. So the reaction quotient Q, right, has the exact same expression as the equilibrium constant K. So right, how I write out Q equals what is the exact same way as I write out K equals what, right? So products over reactants, rates that are stoichiometric coefficients, ignoring solids and liquids, right? So it's the exact same expression, okay? Q just is at a non-equilibrium concentrations of reactants and products, okay? K is the expression, and the numerical value for K is given by the equilibrium ratios of reactants and products. Q can have any value it wants, just depends on what is the current concentration of your reactants and products. Okay, so the numerical value for Q is different all the time because it depends on what is the current concentration of your reactants and products. The numerical value for K is the same for a given chemical reaction, right? For a given reaction, K is always a given number, no matter what your initial concentrations of reactants and products are. But Q differs depending on what your current concentration of reactants and products are. Okay, so why do we care about this Q? Why do we calculate it? Things like that. Well, we can use the reaction quotient and its relationship with K to determine what's going to happen in our chemical reaction. Okay, let's say I'm about to set up a chemical reaction and I mix some amount of reactants and products together, and I want to know, will I get more products or will I get more reactants, or is this mixture of reactants and products already at equilibrium? And to do that, I would calculate the value of Q and compare that with my equilibrium constant K, right? So if I have some concentration of reactants and products, right, I plug in those numbers into my expression for Q, calculate its numerical value, and I find that Q equals K. What does that tell me about my reaction? That it's at equilibrium, exactly, right? So if Q is equal to K, the reaction is at equilibrium. Okay? Right? And what about if Q is less than K? Right? So yeah, so right, it's not at equilibrium, so it's got to do something, right? Every chemical reaction wants to reach equilibrium. Okay? Every chemical reaction, when you start it, will end at equilibrium. Okay? Every reaction always will eventually reach chemical equilibrium given enough time. Okay? So if I have some chemical reaction where I plug in to my expression. Oh, the question? Oh. Maybe not. Hello? All right. There's a question. Feel free to speak. Right. So every chemical reaction wants to reach equilibrium. So if I plug in, given some concentration of reactants and products, into my expression for Q and get a number, and I find that the value of Q is less than K, right? That means the reaction will form more, and what was it that people said? Form more products, right? And then similarly, right, if Q is greater than K, the reaction will form more reactants. Okay? Right? Oh, what the heck? Why is what? How is that not appearing on that slide? All right, let me stop that. Yeah, plain. Try this again. There we go. All right, now let me share this with Zoom. All right, right. And again, we can think about this right, when you're comparing Q with K, think about, right, the numerator are the products, denominator are reactants, right? So when Q is less than K, that means I got too much stuff in the denominator and not enough stuff in the numerator, right? So if my reaction is going to reach equilibrium, it's got to make more stuff into the numerator, which in the numerator are your products, right? So it's got to make more products in order to increase the value, right, the size of the numerator, right, to make Q a larger number, okay? And it will keep on making products until you reach a ratio of products to reactants and give you the equilibrium constant value K, and then you're at equilibrium, and then the concentrations of your reactants and products no longer change. Okay. Similarly, if Q is greater than K, I got too many products, right? My numerator is too big, so I'm going to use up some of those products to form reactants until eventually I reach equilibrium, in which case Q will equal K, right? And the net concentrations of reactants and products will stop changing, okay? Because I've then reached equilibrium. Questions about the reaction quotient Q, what it can tell us, what directions reactions go. Yeah.
Q's kind of like at any given time, their equation, and K is for equilibrium.
Yep. Yeah, so exactly. So, right, so question, right, was just clarification, right, that Q is for any concentration at any time, and that is true. K is only for equilibrium concentrations, okay? So if you want to plug in numbers into K, concentrations into K, you have to plug in the equilibrium values, but for Q, you can plug in any values you want, okay? But yeah, but for K, like in the example problem, right, that we did, okay, here we go, right? We plugged in, right, an equilibrium mixture, so we plugged in the equilibrium partial pressures into the equilibrium constant expression to find the equilibrium partial pressure of Cl2, okay, right? If these were some initial pressures and not necessarily the pressures at equilibrium, then I won't be able to just plug those into K to solve for PCl2 because those pressures wouldn't be the equilibrium value, right? And we'll do some examples of that potentially today, starting, and then plenty more on Wednesday showing that, okay? Other questions about what we've covered so far, right? Equilibrium constant expression, numerical value, the fact that it's unitless, right? Reaction quotients, manipulating reactions and how that affects the equilibrium constant. All right. So here, just do an example for reaction quotient Q here. So at 100 degrees Celsius, I have an equilibrium reaction which has a numerical value for its equilibrium constant equal to 2.19 times 10 to the minus 10. And the question is the following mixtures of reactants and products an equilibrium mixture? And if not, what direction must the reaction proceed to achieve equilibrium? I'm just flipping over to this, the exact same question, right? Right, so if I want to determine, right, if this is at equilibrium, right, we need to calculate Q. What is going to be the expression for Q for this reaction? And then what? So you have Cl2, CO. What are we missing? And where does COCl2 go? Oh, well, you count. Sorry, I forgot I froze the screen. Thank you. Ah, makes a big difference. Like, what the heck is he talking about? All right. Yeah. Divided by COCl2. Thank you. Sorry about that. Forgot I froze that screen. Right. So Q, right, is the exact same expression as K. And the expression for K as well as Q, right, is the concentration of Cl2 times concentration of CO divided by concentration of COCl2. So, right, to solve this problem, right, whether or not we're at equilibrium, given the equilibrium constant here, we just got to calculate the value of Q, right? So we plug in the concentration of Cl2 is 6.62 times 10 to the minus 6. Concentration of CO is 3.3 times 10 to the minus 6. And the concentration of COCl is, or COCl2, sorry, is 2.0 times 10 to the minus 3. Okay. So I just got all those values from up here, right? So I just plugged in for what was given in the problem. Okay, when you plug in all those numbers and simplify, you will get 1.09 times 10 to the minus 8. Okay, so is Q greater than or less than K? It's greater than K, right? While Q is a very small number, 1.09 times 10 to the minus 8, it's still larger than K, which is 2.19 times 10 to the minus 10. So Q is greater than K. So what will happen in order for this reaction to reach equilibrium? Right, it's going to go to the left. It's going to form more reactants, right? And right, which, as we'll talk about with Shortly's principle on Wednesday, right? That means it will go to the left, right? So when you say go to the left, it means, right, you look at your chemical reaction, going to the left is going towards reactants, right? So this reaction will go to the left, right? It will form reactants, right? Going to the right is forming products, right? So the products are on the right side of the reaction, reactants are on the left. Questions about this example? All right, so same problem, just now different concentrations, okay, for COCl2. Right, again, the reaction was COCl2 forming CO plus Cl2, okay, and that equilibrium constant, right, was that 2.19 times 10 to the minus 10. Okay. Okay. So for this, same question, right? Is this at equilibrium? If not, right, what do I have too much of? What direction is it going to be going? So here's people saying C. Any other? Some B's, some C's. All right, right. So if you plug in to right Q here, let me swap over this real quick. All right, so if you plug in to your Q expression, right, your reaction quotient expression Q here with the values given, you'll get Q equals 5.5 times 10 to the minus 12, I believe. If I did my calculations correctly, right? Which, if I compare that to K, Q is going to be smaller than K, right? And if Q is smaller than K, right, then I have too many reactants, and so it's going to proceed to the right to form products, right? Because again, Q and K both are products of a reactant, so Q is too small. That means I got too much stuff in the denominator, not enough stuff in the numerator. So I got to use up some of my reactants to form products. Okay. So again, too many reactants. C here. We're going to proceed to the right to form products. Okay. And C for this question. Questions about this? So I think that example is going to start talking about ice tables. And given the time left, I don't want to start talking about that. So on Wednesday, we're going to talk about ice tables and do plenty of examples of those, as well as talk about Le Chatelier's principle. Okay, and that will do it for chapter 15. Right. For those who are here in class, if you would like to pick up your exam 1, you're welcome to do so. I have the exams not alphabetized, but broken out into form 3 or 4. For those who remember their form numbers, I'll set it down here on the table. And don't forget to turn in your participation questions on the back table as you're leaving. For those here on Zoom, is there anyone that has any questions before I close out the Zoom session? All right. I don't see any questions, so I'm going to close out Zoom, and I'll see you guys on Wednesday.